welcome to this problem walkthrough. Today, we'll be tackling LeetCode problem number 1009, complement of base 10 integer. This is a fun and practical bit manipulation problem that challenges us to compute the bitwise complement of a non-negative integer. Stick around as we break it down step by step and unravel the solution together. Every non-negative integer can be represented in binary, where each digit is either a 0 or a 1. The complement of a binary number is determined by flipping all of its bits, converting every 0 to a 1, and every 1 to a 0. Now, for any given integer n, the task is to find the complement of its binary representation, but only within the range of its most significant bit to its least significant bit. The result of this operation should then be converted back into a base 10 integer and returned. For example, if the input is 5, the output would be the complement of 5's binary form, expressed as a base 10 number. The input will always be a single integer, ranging from 0 to 10 to the power of 9, and the output should also be a single integer that represents the complement. To understand this with an example, consider n equals 5. The binary representation of 5 is 101. When we flip all the bits, 1 becomes 0 and 0 becomes 1, resulting in 010. This binary number, 010, corresponds to 2 in base 10. So, for an input of 5, the function should return 2. Another example is n equals 7. The binary representation of 7 is 111. Flipping all the bits gives 000, which is 0 in base 10. Therefore, for an input of 7, the output is 0. Let's look at a third example, n equals 10. The binary representation of 10 is 1010. When we flip all the bits, we get 0101. This binary number corresponds to 5 in base 10. So, for an input of 10, the function should return 5. Additionally, there are some constraints to keep in mind. The input n will always be a non-negative integer, and it will not exceed 10 to the power of 9. This means the function must handle numbers up to 1 billion efficiently. The binary complement is defined strictly within the range of the number's most significant bit to its least significant bit, so the solution should respect this range when flipping bits. For edge cases, consider when n equals 0. The binary representation of 0 is simply 0, and flipping this bit gives 1. Therefore, the complement of 0 is 1. Another edge case is the largest possible input, n equals 10⁻9. The function must handle such large inputs and compute the complement efficiently. For a smaller input like n equals 1, the binary representation is just 1, and flipping the bit gives 0. Lastly, numbers with leading zeros in their binary representation, such as n equals 4 with binary 100, should be handled correctly. The complement in this case would be 011, which is 3 in base 10. These examples and edge cases emphasize the importance of accurately flipping bits and handling a wide range of values, ensuring the function behaves as expected for all valid inputs. To solve the problem of finding the complement of a base 10 integer, we need to flip every bit in the binary representation of the given integer n. In other words, all 0s should become 1s, and all 1s should become 0s. One approach we considered is the brute force method. The idea here is to convert the number n into its binary representation as a string, iterate through each bit, flip it, and then convert the flipped binary string back into a decimal number. For example, if n is 5, its binary form is 101. By flipping the bits, it becomes 010, which corresponds to the decimal value 2. While this method is conceptually straightforward, it involves string manipulations that require additional space and time proportional to the number of bits in n. This makes it less efficient compared to other methods. An alternative and more optimized approach uses bitwise operations directly. Instead of converting n to a string, we can construct a mask with all bits set to 1 for the same length as n's binary representation. Then, we can XOR n with this mask to flip all bits efficiently. This eliminates the need for string manipulations and improves both time and space complexity. The optimized bitwise approach is implemented in a few simple steps. First, we determine the number of bits in n's binary representation. For example, if n is 5, its binary form is 101, which has 3 bits. Next, we create a mask with all bits set to 1 for this length. This is done by left-shifting the number 1 by the bit length and then subtracting 1. For instance, with 3 bits, 131 gives us 7, which is 111 in binary. Finally, we compute the complement by XORing n with the mask. This operation flips all bits of n efficiently. The time complexity of this approach is constant, 1, because the number of bits in n is limited, and the operations are performed in a fixed number of steps. Similarly, the space complexity is also 1, as no additional data structures are required. This approach is both elegant and highly efficient. It avoids the overhead of string conversions while ensuring scalability for larger integers, making it an ideal solution. For these reasons, the optimized bitwise approach was chosen as our final strategy. The key insight, or aha moment, in solving this problem was recognizing that the bitwise complement of n can be calculated by XORing it with a mask of all 1s that matches the length of n's binary representation. This insight allowed us to bypass the need for intermediate string conversions, simplifying the process significantly. By constructing the mask using the formula 1 bits 1, we ensure that the mask automatically adapts to the size of n. This eliminates the need for manual handling of different bit lengths. When comparing the two approaches, the brute force method has the advantage of simplicity but falls short in efficiency due to the overhead of string manipulations and additional space usage. In contrast, the bitwise approach is optimal both in terms of time and space, making it the preferred method for this problem. The final solution, as shown in the Python code, begins by checking if n is 0. If so, the complement is 1, as 0 has no bits to flip. Otherwise, we calculate the bit length, construct the mask, and use XOR to compute the complement. This concise and efficient implementation demonstrates the power of bitwise operations in solving problems like this one. To solve the problem of finding the complement of a base 10 integer, we need to start by understanding its binary representation. Every integer in base 10 has an equivalent binary form, where each bit represents a power of 2. For example, the base 10 number 5 is represented as 101 in binary. The complement of a binary number is obtained by flipping all its bits, changing each 1 to a 0 and each 0 to a 1. So, the complement of 101 is 010. To compute the complement, the first step is determining the number of bits in the binary representation of the given integer n. This can be identified from the position of the most significant bit, or MSB, which is the leftmost one in the binary number. For instance, for n equals 5, the MSB falls at the third position from the right, which means 5 has 3 bits. Using this information, we can proceed to generate a binary mask of the same length as n, where every bit is set to 1. For example, the mask for a 3-bit number like 5 would be 111 in binary. The mask is crucial for calculating the complement, and it can be efficiently generated using the formula mask equals 1 number underscore bits 1. Here's how this works. The operation 1 number underscore bits shifts the binary number 1 to the left by number underscore bits positions, appending the appropriate number of trailing zeros. Subtracting 1 from this result converts these trailing zeros into ones, giving us the desired mask. For example, if number underscore bits equals 3, then 13 results in the binary number 1000, and subtracting 1 gives 111, which is the mask. Once the mask is created, we use the XOR operation to compute the complement of n. XOR, or exclusive OR, is a bitwise operation that flips a bit when it is paired with a 1. By XORing n with the mask, we effectively flip all the bits in n. For example, if n equals 5, binary 101, and the mask is 111, the result of n caret mask is 101 XOR 111, which equals 010 in binary, or 2 in decimal. The final result of the XOR operation gives us the complement of n in decimal form. This approach is both efficient and intuitive, leveraging bitwise operations to avoid unnecessary conversions between binary and decimal formats. This algorithm is robust enough to handle edge cases. For instance, if n equals 0, the binary representation is simply 0, and its complement should be 1. This is because the mask for a single-bit number in this case is also 1. Additionally, the algorithm scales well for large values of n, as the mask generation depends only on the number of bits in the binary representation of n, not its magnitude. From a data structure perspective, the algorithm is quite efficient, as it operates directly on integers without requiring any auxiliary data structures. The key operations involved include calculating the bit length of n, generating the mask, and performing the XOR operation. Calculating the number of bits in n can be done using the built-in method n.bit_length, which determines the position of the most significant bit. This operation has a time complexity of O log n, because the bit length of a number is proportional to the logarithm of its value. Generating the mask using the formula 1 number_bits, 1 is a constant time operation, as it involves only a single shift and subtraction. The XOR operation, which computes the complement of n by flipping its bits, is also a constant time operation since it works directly on the binary representation of the integer. Combining these steps, the entire algorithm can be summarized as follows. First, check if n is 0, and if so, return 1. Otherwise, calculate the number of bits in n using n.bit_length. Next, generate the mask using the formula 1 number_bits, 1. Finally, compute the complement by XORing n with the mask and return the result. The pseudocode for this algorithm is straightforward. Define a function bitwise complement that takes an integer n as input. If n equals 0, return 1. Otherwise, calculate number_bits as n.bit_length, generate the mask as 1 number_bits, 1, and return the result of n_mask. The algorithm's efficiency lies in its simplicity and reliance on bitwise operations, which are both fast and memory efficient. Analyzing the algorithm's complexity, the time complexity is dominated by the bit length calculation, which is O log n. Both the mask generation and XOR operation are constant time operations, O(1). Therefore, the overall time complexity of the algorithm is O log n. In terms of space complexity, the algorithm does not use any additional data structures, as all operations are performed directly on integers. This results in a space complexity of O(1). The combination of logarithmic time complexity and constant space complexity makes this solution highly efficient, even for large inputs. By leveraging the properties of binary numbers in bitwise operations, the algorithm achieves an optimal balance of performance and simplicity, making it a robust and elegant approach to solving the problem of finding the complement of a base 10 integer. The solution to LeetCode problem number 1009 complement of base 10 integer is implemented as follows. 1. We start by handling the special case where the input n is 0. If n is 0, the complement is defined as 1, so we immediately return 1. 2. For all other values of n, the goal is to compute the complement by flipping all bits in the binary representation of n. To achieve this, we first calculate the bit length of n using the bit_length method. This gives the number of bits required to represent n in binary. 3. Using the bit length, we construct a bit mask where all bits are set to 1 and the length matches the binary representation of n. The bit mask is created by left shifting 1 by the bit length and subtracting 1. For example, if n equals 5, binary 101, the bit mask will be 111. Finally, we compute the bitwise complement by XORing n with the bit mask. This effectively flips all bits in n's binary representation, giving us the desired complement. 5. The result is returned as the complement of the base 10 integer n. This approach is efficient, with a time complexity of O(1), since the operations depend only on the bit length of the input number, and the bit length is bounded by the system's integer size. The space complexity is also O(1), as no additional data structures are used. This is the Java implementation of LeetCode problem number 1009, complement of base 10 integer. The logic mirrors the provided Python implementation. Key differences include Java-specific syntax, such as using integer to binary string n.length to determine the number of bits in the binary representation, and explicit type declarations. The method calculates the bit mask based on the binary length of the input n, and computes the complement using the XOR operation. We start with an input number, n equals 5. The first step is to handle the edge case where n is 0. If n is 0, we directly return 1, as specified in the problem. However, since n is 5, we move forward. Next, we calculate the bit length of n. The binary representation of 5 is 101, which has a length of 3 bits. Using Python's built-in bit_length method, we determine this value. Once we have the bit length, we create a bit mask. A bit mask is a number that has all bits set to 1, with the same length as the binary representation of n. For n equals 5, the bit mask is created using the formula, 1 left shifted by the bit length, minus 1. This evaluates to 7, which in binary is 111. The binary representation of the bit mask is 111. Now, we compute the complement of n by performing a bitwise XOR operation between n and the bit mask. For n equals 5, this XOR operation is 5 XOR 7. In binary, this looks like 101 for n, XORed with 111 for the bit mask, which results in 010. This is the binary representation of 2. So, the complement of 5 is 2. Moving to a new example, when n is 10, we begin again by checking if n is 0. Since n is not 0, we proceed. For n equals 10, the binary representation is 1010, which has a bit length of 4. Using the same process as before, we calculate the bit mask. This is done by taking 1, left shifting it by the bit length, and subtracting 1. For a bit length of 4, this evaluates to 15, which in binary is 1111. Now, to compute the complement, we XOR n with the bit mask. For n equals 10, the XOR operation is 10 XOR 15. In binary terms, this is 1010 XOR 1111, which results in 0101. This is the binary representation of 5. So, the complement of 10 is 5. Finally, let's look at the case where n equals 0. In this case, we directly return 1 without any further calculations. This is because the problem explicitly defines the complement of 0 as 1. Therefore, the output for n equals 0 is simply 1. With these examples, we've seen how to handle different cases, from the calculations for non-zero numbers to the edge case where n is 0. To analyze the time complexity of the bitwise complement function, we can break it into individual steps. First, checking if n equals 0 is a straightforward comparison, which takes constant time, or O1. Next, the n.bit_length method calculates the number of bits needed to represent n in binary. Since the number of bits is proportional to the base 2 logarithm of n, this operation has a time complexity of O log n. Then, we compute the bit mask using 1_bit_length 1. The left shift operation is effectively constant time because the number of shifts is small, and the subtraction is also O1. Finally, the XOR operation n_bitmask processes each bit of n, which again scales with the number of bits, or O log n. Combining these steps, the dominant factors are the bit_length calculation and the XOR operation, both of which are O log n. Therefore, the overall time complexity of the function is O log n. Now, let's look at the space complexity of the bitwise complement function. The input n is stored as an integer, which takes constant space, or O1. Additionally, the intermediate variables used in the function, bit_length and bitmask, are also integers, each requiring O1 space. Importantly, the function does not create any additional data structures, such as arrays or strings, nor does it use recursion, which means there is no extra memory overhead. As a result, the overall space complexity of this implementation is O1. When comparing different approaches to solving the problem, a naive method might involve converting n to its binary representation as a string, flipping each bit manually, and then converting the result back to an integer. This naive approach includes converting n to binary, which takes O log n time, iterating through the binary string to flip bits, which also takes O log n, and finally converting the flipped string back to an integer, again O log n. While this approach has the same time complexity of O log n, it is less efficient due to the overhead of string manipulations. Moreover, it requires extra space proportional to the number of bits in n, or O log n, space. In contrast, the optimized implementation avoids string manipulation by using direct bitwise operations, resulting in a time complexity of O log n and a significantly better space complexity of O1. In summary, the optimized approach to solving this problem uses bitwise operations to achieve a time complexity of O log n and a space complexity of O1. This makes it both time efficient and space efficient when compared to naive methods that rely on string conversions and additional memory. By directly working with the binary representation of n without creating intermediate data structures, this implementation stands out as a clean and optimal solution. One common mistake when solving this problem is using the wrong mask for flipping the bits. If the mask doesn't match the number of bits in the input n, the complement will be incorrect. For instance, using n directly might seem tempting, but it assumes an infinite bit width, which leads to incorrect results. The correct approach is to use 1n.bit_length, 1, which creates a mask with the exact number of bits as n. Another issue arises with edge cases, like when n equals 0 or 1. The complement of 0 is 1, and for 1, it's 0, so these scenarios need to be handled explicitly to avoid any off-by-1 errors. Additionally, there can be confusion between binary and decimal representations. For example, some solutions attempt to flip bits by manipulating the binary string directly. However, this approach is slower and more error-prone. Instead, it's better to stick to bitwise operators for efficiency and simplicity. Another mistake is overcomplicating the solution. Some attempts involve manually constructing the binary complement using loops or string transformations, which is both verbose and inefficient. Instead, leveraging Python's bit_length and bitwise operations can simplify the implementation significantly. Additionally, for those working in languages like Java, it's crucial to account for signed integers. In such languages, a bitwise NOT operation can introduce negative numbers due to the sign bit, which is not aligned with the problem's assumption of non-negative integers. To address this, masking the bits appropriately ensures we ignore the sign, leading to a correct solution. By avoiding these pitfalls, you can ensure your implementation is both efficient and accurate. To excel in interviews, it's important to focus on the binary representation of the number and rely on bitwise operations for a clean and efficient solution. Avoid unnecessary conversions between binary strings and integers, as they add complexity without any real benefit. A common pattern to recognize is that the complement of n is achieved by flipping all its bits within the range of its bit length. This concept often appears in other bit manipulation problems as well. In terms of efficiency, the optimal solution runs in O log n time, as the bit_length operation scales with the number of bits in n. During interviews, it's also helpful to clarify any constraints on the input size and to confirm how edge cases like n equals 0 should be handled. For further practice, related problems such as LeetCode 476, 191, 338, and 461 can help you refine your understanding of bit manipulation techniques. There are alternative approaches to solving this problem, each with its own trade-offs. One method is using string manipulation by converting n to its binary representation, flipping the bits manually, and then converting back to an integer. While this approach is easier to understand, it's less efficient and more error-prone, especially for larger inputs. Another option is a mathematical approach that involves computing 2k1, where k is the bit length of n, and then subtracting n from this value. This avoids explicit bitwise operations but requires careful handling of powers of 2, making it less intuitive. Finally, language-specific optimizations can also simplify the implementation. For example, Python's operator or Java's integer.highest1bit can help streamline the process. However, relying on language-specific behavior might not always generalize well, especially in an interview setting. Each of these methods has its place, but understanding the trade-offs is key to selecting the best approach for the problem at hand. Great job making it to the end of this walkthrough. We covered the bitwise complement of a base 10 integer, explored its time and space complexity, and discussed key takeaways. Remember, mastering bit manipulation is a valuable skill for technical interviews. Thanks for watching, and see you in the next video. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!